Okay, I think we have a quorum. Kat, I think everything should be okay to record, right? Okay, sounds good. So let's get started. Welcome everybody to another Ignition community meeting. Thank you for everyone being here. This is the first meeting of 2022. Exciting. We have two presentations today, one about the Pan-African robotics competition and another one about setting up CI using Ignition on GitHub Actions, also using ROS 2. But before we get to that, just a few reminders. Everybody feel free to add your name to the attendees list. We're going to go over a few announcements for a little bit, then we get into the presentations. Then if we have time, we go over some news that Kat curated for us. And at the end, if anyone else has something that they'd like to discuss, feel free to add items to the agenda. We'll be sure to make time for it if we're running out of time. Sounds good. So starting with the announcements. So a few things that just to let people be aware of. First is that we started making minor and patch release announcements on Gazebo community. This is new. We until now we would only announce like the big major releases of a new Ignition collection, but now we are actually making periodic announcements with like minor releases, so you can see the things that are coming in minor and patch releases. So keep an eye on this releases category on Gazebo community. We're going to be posting there periodically. Another thing that people may be interested in is that there is a proposal for a maritime robotics working group on ROS Discourse right now, and the scope includes Ignition Gazebo and Gazebo Classic. So for folks in the maritime community, if you're interested in simulating these robots a little bit better and contributing and using the software, be sure to check out this thread, sign up for the working group. And finally, people in the self-driving vehicle space may have noticed that the LG sunsetted their SVL simulator. It's open source, it's going to be there, but they are not going to be supporting it anymore. With this, like we were wondering if people are interested in vehicle working group for Ignition, or if there is like people out there who are already simulating self-driving cars in Ignition who would like to get in touch with us or put out a demo, share some resources so people can have a stepping stone to get started with self-driving cars in Ignition. So if you have interest, feel free to reach out directly to me or to Kat, and we continue from there. Or even like start a post on Gazebo community or something like that. That's it for announcements. So I think we can get started with our month's focus, and the first presentation is going to be by Kenny, who was the lead of the Pan-African robotics competition. That it was a huge competition that used Gazebo Classic, included more than 30 countries, lots of exciting stuff going on there, and he's going to tell us all about it. So Kenny, thank you for accepting to be here and presenting for us, and you can share your screen and get started.
Awesome, thank you. Is my audio coming through?
It is.
All right, great. Let me just get up my, okay, can you see my screen?
Yes.
Yes, all right, great. Well, hi everyone. Yeah, thank you, Louis. Thank you everyone for the opportunity to speak here at the community meeting today. So I'll be sharing our experience running the virtual robotics competition using Gazebo and ROS for Park. Okay, and so the structure of the talk would be as follows. I'll start by giving a little background about myself, and then I'll introduce Park more formally, and then I'll describe the work that we did in 2021 in the virtual competition. Then I invited the team lead of the winning team from the competition to share a little bit about his experience, and so we hear that. And then I'll conclude with what we're thinking about future iterations of Park, both virtually and in person. And then I hope that we have enough time to get feedback actually from the community. There are a lot of smart people here today, and I really want to hear comments, recommendations, feedback of how we can improve and use some of these tools better in the future. All right, so about me, my name is Kenechukwu Mbanisi. My day job is doing research in robotics. I'm a PhD candidate at WPI. And my research is in shared autonomy, but besides that, I'm very passionate about STEM education, particularly how to use robotics to inspire the next generation of engineers and innovators, and especially from the African context, actually. And so because of that, working with Park as a coordinator of the Engineers League was an awesome opportunity for me that I really enjoyed being part of and continue to do so. So Park stands for Pan-African Robotics Competition. It was founded in 2015. And the goal is really simple, just to inspire STEM on the African continent. And so every year we have the competition hosted in a different country on the continent as when possible across 4 categories. So we have the Tech League, which is focused on middle schoolers. The Stars and the Makers League are focused on high school students. And then the Engineers League, which is the one I was coordinating, is for college level students and engineers, professionals, whoever above college level. So since its founding, Park has grown phenomenally. In fact, it has over 1,000 participating students, and we have teams from over 30 countries in Africa. And actually, I think 2 years ago, before the pandemic, we had a team from the US actually participate in Park. And so it's been very exciting to see how progress has been. And a lot of that progress has been made possible by the amazing line of sponsors that we have over the years. And I'm just showing a few of them here. I put in here just the website, and I think it's also in the documentation for this meeting if you want to check it out later on. So I included a few videos here also just to give you a feel for how the competition runs generally. We have teams from all over Africa come together to learn and build and compete together. At the event, if you're at the event, it could feel like a FIRST Robotics or a VEX Robotics competition, if you're familiar with those in the US here. But Park is somewhat distinct in that every Park edition is designed around a theme that captures some of the emerging needs or challenges that we're looking to explore in Africa. And the goal is then to inspire students and people on the continent to really think about how to use technology to solve those problems. And then the video here on the right that just started playing is a gaming environment that was designed in-house by Park for the virtual version of the Stars and Makers League. That's for the high school students. And so this was because this was in response to COVID last year. We couldn't do something more typical in person. So this was designed, teams could still custom design their robot and still compete with each other in some of this kind of problems in this environment. So I think this is really, really neat stuff. So I'm going to move on here anyways to talk about the virtual challenge. And so that's the Virtual Engineers League competition. And so the theme that we had for the year last year was future work. And what we were thinking was inspiring teams to think about how technologies will govern the future, the way society will function in the future, and how they can start to think about how to design these kind of systems today, right? So we focused on the problem of last mile delivery. And so the teams were asked to develop software to deploy and monitor an autonomous wood mobile robot for parcel delivery operations. So that was the theme that we had for last year. The format was as follows. We had 2 phases, right? The first phase was completely in simulation, where the teams built their software solution to control the robots, navigation in Gazebo and ROS. The top performing teams then advanced to the second phase, where they got a chance to work on a physical robot, right? To test and refine the software solution in a real mock-up environment towards the final competition day, which was, and all of this was performed remotely. Teams were all over different countries in Africa, and our main base was in Senegal, in West Africa. And so we had about 40 teams participate in the simulation phase. About 6 teams qualified for the physical robot phase, and on competition day we had 1 winner. So just to give some more details about the phases, the first phase we had all the teams participate, in simulation, and so we had developed ROS packages and Gazebo files for the competition. We designed this mini city world file in Gazebo with characteristic features like a sidewalk, obstacles, traffic signal, and we have a park here. And the goal was for the high-level goal was for the teams to write software to safely navigate the robot from this pickup location here, to stay under the sidewalk, follow traffic signals, go into the park, and deliver the parcel to the person here. And so that was the general high-level goal here in simulation 1. In the first phase, all the teams were able to download this packages from GitHub and run on that locally and submit their solutions. We used the Agile X Scout robot as our delivery robot in this case, and we got support from them as well for this, and that was great. So we broke down the delivery task into 3 subtasks, if you will. Sidewalk following and obstacle avoidance, and then sign detection, recognition to obey traffic signs, and then the last was just go-to-go motion navigation task. So those are the 3 tasks that we had, and we had teams actually solve these problems independently and submit solutions for them, and that kind of helped them to be able to learn more specifically about these different code behaviors that an autonomous delivery robot should be able to effectively do. We definitely removed a lot of complexity from the problem because of the background, a lot of the teams that we're getting, and so we added a lot of things to just make it a little bit easier and tractable for them within the time frame. In the second phase, the qualified teams were able to test and refine their software on the physical robot. We had a couple of unexpected events, some COVID-related, some others, but we had to pivot from our original plan of building a more elaborate city setup to something smaller, you can see here. So we had to do it indoors and just use cardboard and wood to set up something that could give us the proper structure that we could use to simulate the delivery task. And so we opted for a smaller robot for a delivery scenario here. So we use a Turtlebot 3 for that. And so the task, again, same thing, was to navigate from the start location to the goal location, and do it safely, follow traffic signs, and stay on the sidewalk. That was really what the goal was there. And because the teams were all remote and they had limited time to test and develop their software, we actually created another simulated version of this markup environment in Gazebo to allow teams to iteratively test different parts of the solution before deploying. And so what we had was, teams could sign up for specific times in the day over a stretch of around a month or 2 months to come online and test in the physical robot, and otherwise they could be storing ROS bags with data or just testing in simulation as well. And so here I'm just showing what some of that looked like. This is actually an image of a GIF from one of the team's final solution testing in simulation. And then on the physical robot day, we had teams try to test and run the solutions. Providing remote access for teams to interface with the physical robot was, from anywhere around Africa, was actually quite challenging. It was more challenging than I had expected. I think it was primarily because of internet availability, I think. So the approach that we sort of set it on for this iteration of the competition was as follows. So we had teams, i.e. remote PCs, connect to a host PC that was local in Senegal using remote desktop, for example, TeamViewer. And once they were local on that computer, then they could use SSH to communicate with the robot that was within the shared network there. So I think this worked fairly okay, not as reliably as we expected or wanted it to. But I think that might also have to do with internet limitations as well. So I'm happy to actually hear from the community maybe different ways that we could address this problem, because this was one of the main bottlenecks in really getting the teams to explore as much as possible on the physical robot. So, but yeah, so then this is actually footage on the final day. So the teams presented their solution. They did, presentation slides to show their methodology and how they went about solving the problems. And we had an amazing panel of judges who were there to evaluate and award points. And so actually the winning team was Team Asimov from Ghana. And I have the team lead of that team here, Evans, and the Evans will just share a little bit about his experience, his team's experience participating in the competition. So Evans, are you there? Okay.
Yeah. No. All right. So, thank you, Kanechukwu. So let me briefly talk about our experience while we're working on this competition. But before, let me just introduce the members of the team. Like Kanechukwu said, my name is Evans Jangba. I was a team lead for Team Asimov. And then I'm actually a mechanical engineering graduate, and I have interest in robotics, embedded systems. And my other teammate was Isaac Atia. He was interested in he's an electrical engineer, and he has interest in computer vision, AI, and drones. If you could go to the next slide. Right. So let me talk a little briefly about our experience overall, what we're doing or what we found out while we're doing the challenge. The very first encounter was the learning curve. Prior to actually registering for the competition, between us, we had about 6 months of ROS experience, which was really tasking because ROS can be a little bit difficult to learn if you're coming from a non-software development background like I was. So it was a little bit hard to catch up to. But then, luckily, there was an amazing community on Reddit, on the ROS Asks, I think, the ROS Wiki, basically community platform for asking questions and all. There's an amazing community there that supported. I could ask questions and I could get answers as quickly as possible. So it made the learning relatively straightforward. If you ask a lot of questions, you get a lot of support and answers back. And also within the competition, we had a forum where we could ask questions, and Kanechukwu was on hand to answer a lot of these questions. So that really aided our learning and helped us really catch up with ROS and Gazebo really quickly. And the other one was simulation setup, and this was really key for me because before then I'd worked a little with Gazebo, but I didn't really have a good idea of the extent of what Gazebo could do. So seeing the whole, should I say, world set up within Gazebo was really, really, really interesting. Right? It piqued my interest a little bit because prior to that, all I knew about Gazebo was basically you place your robots in the world, and then you turn on a couple of sensors, you place a couple of blocks here and there to check whether the sensors work. And I really had no idea you could simulate things like traffic lights or even placing custom models like the zebra crossing and the other stuff that we're placing there. Right. And one other thing that really supported our learning was the amount of online resources that were available on YouTube. And I've mentioned some of them being the ROS Wiki, and then the Gazebo Asks as well, and and Reddit. But there are also resources on YouTube, a lot of resources that helped us learn. I remember before the competition got started, I didn't really have a lot of experience with computer vision, practically nothing at all. I hadn't done any computer vision project at all whatsoever. So I quickly went online to YouTube, and I found a very extensive tutorial series on computer vision and OpenCV, and within a couple of weeks, we're basically up to task, and we could set up computer vision tasks for our robot. So the whole overall thing was really, really eye-opening, because it opened us to the vast possibilities of out there in terms of approaching robotics, which was vastly different from what I was used to and knew. Right.
Awesome. Thanks, Evans. It was a great learning experience for a lot of the teams, and even for me as well. Just being part of that learning curve for them was awesome. So we have just a few more minutes and talk a little bit about some of the lessons learned and what future iterations we're looking to incorporate some of those lessons and things we're interested to do. I think one of the things that we will be doing going forward is to streamline the process and provide more scaffolding, if you will, for teams. A lot of the teams, like everyone's mentioned, had no prior experience using ROS and Gazebo, and some teams actually even using Linux, like running on a Linux computer. So that was, in a sense, challenging, but also exciting for me, because what we were doing at Park was their first exposure to robotics at this scale, or at least using some of these open source, really important tools. So that's a great opportunity for learning and for teaching them. But in any case, getting up to speed was challenging, right? So in future iterations, looking about how to Dockerize that process, excuse me, to shield away some of the installation, system setup requirements and whatnot. And then the other thing is in the simulation phase, also using cloud-hosted simulation platforms that may be out there existing. I think Open Robotics supports this, I guess, for some of the competitions. I would like to hear that if that is the case. It's something that I would definitely love to talk or explore about. And in terms of challenges, we're looking to to explore this other options in terms of kind of problems we can pose to teams. For example, drone navigation, something I think would be a great one for our next, maybe after this year, the next edition. Really inspired by this company here, Zipline, if you're familiar with them. They essentially provide last mile delivery of essential services, like medical essential services on the African continent in a couple of countries. And so doing something within that space that allows teams to really grapple with this kind of problems would be great, to just expose them to how technology can really solve problems. So with that, I would like to just acknowledge all the Park teams, the founder and the coordinators, and my personal team that supported in making it possible, the judges and the actual teams that participated last year. And thank you for listening. And I'm inviting us to share today. I just put down here 2 prompts, and if we have any amount of time, I'm honestly interested in hearing from the community what ways we could improve our approach and how we could better leverage Gazebo, Ignition, and open source tools going forward. So with that, yeah, thank you very much for your audience, and yeah, thanks.
Nice. Thank you for the presentation, Kenny and Evans. That was very good. Does anyone have questions for them? So we can try to answer some of your questions, Kenny. So, how to leverage Ignition, Gazebo, and other open source tools. Speaking for Ignition, Gazebo, I think that one thing that you may encounter with approaching it for the first time is that it has way less examples and documentation than the Gazebo Classic. So that thinking from that front, it may be a little bit more difficult for a beginner to get started. But thinking from a different angle, Gazebo Classic is not going to be supported beyond 2025. So, it's really like if you're preparing the students for the future and for like some tools that they are going to use in their job in the future, it may be worth looking into the more modern ones. It's a similar situation with ROS 1 and ROS 2. You guys were using Melodic, right?
Mm-hmm.
So it may be worth like looking into ROS 2 as well, which is in a similar situation.
Yeah, no, that is a great point. I was actually considering ROS 2. It was like, that's Edwin's, for example, the example Edwin's gave with access to resources would not have been as easy to come by, right? So it's kind of like a chicken and egg problem, I guess.
Yeah, exactly. Yeah.
But thank you.
Also, when you mentioned the cloud, I think it's really a trend to start moving more of these competitions to the cloud and leveraging more cloud resources. The subterranean competition that you mentioned was run in the cloud for teams, and here at Open Robotics, like Nate can talk a little bit more about it if he's here. But we're starting to really set up Cloud Sim as a service that people can use for their own custom competitions and things like that. So keep an eye on that.
Yeah. Great.
Cool, thank you, Kenny. So if people don't have questions, I can go on to the next presentation, and then people can always come back in the end and ask any more questions if there are any. So let me share my screen because I'll be the one doing that. Let's see. Oh man, can I share one? Okay, well, we'll see how it goes. I'll have to share my Gazebo screen and then reshare because I'm on Firefox. Okay, so this presentation now is about setting up simulation-based CI for robots. So to motivate it a little bit, I just wanted to show like a simple robot that we're going to be using to set up CI for. So this is called Dolly. It's a virtual like sheep robot, and it's super simple. All it does is just like follow the first thing that it says in front of it and then stop like about 1 meter behind it. So that's what it's doing here. If we move the lady a little bit forward, the robot goes and follows her there. So it's super simple, and the goal here is to do something as simple as possible, just to exercise various aspects of a more complex robotic system, and then and be able to exercise all of these like different aspects of it to exemplify how to set up a package that uses ROS2 and ignition, and also the focus of this talk specifically is about how to test it. So the scenario that we're going to be looking into here is the use case is someone who has a physical robot that they want to leverage simulation for testing algorithms in that robot and making sure that there are no regressions, that they can develop new behaviors for the robot and not break previous behaviors. So you want to be setting up continuous integration that runs on every commit that you do to that robot's code to make sure that it doesn't regress and break. So this is the use case that I'm going to be tackling now. I know there are various different use cases for simulation, but I think this is one of the most common ones. So I'll be showing you a little bit of how this specific simulation is set up. Then we're going to talk about how, you know, all of the bits and pieces, and then I'm going to jump into the code and show you how it's set up. And then if people have questions, you know, in the end, feel free to raise them. If you've tried setting up a simulation, you had some specific use case that you tried and it didn't work, you know, just let me know. So, you know, just to introduce myself for people who don't know me, I'm Luis Pobel. I'm the technical lead of simulation at Open Robotics. And this presentation is about ignition using ROS2 and GitHub Actions all together to set up some CI. So first, the version of ROS2 that we're going to be using here, that is running here right now in the simulation that I'm showing you, is ROS rolling. It's the bleeding edge, unstable ROS2 distribution. So everything can change at any moment. It's living dangerously, but I think that's, you know, that's fun. And this distribution eventually is going to become ROS humble. that is going to be released in May. And for ignition, so I'm using Ignition Gazebo, which is not, it's the latest generation of Gazebo, so it's not Gazebo Classic. And the version that I'm using here is Ignition Fortress. So why am I using Fortress with rolling? It's because Fortress is going to be the official version to use with ROS Humble that is coming up in May. So this is the officially supported combination right now. If you're using rolling, we recommend that you use Fortress. So that's what I have here. So let's get started. Just to motivate, to understand all of the bits and pieces that are going on here, because if we don't understand the system, it's going to be hard to explain how we test it, right? So I'm just going to give you a quick overview of the system. So here, Dolly follows, right? Dolly has one single sensor, that's a laser. We can visualize it here real quickly. Oops, well, if I close the, yeah, so we can visualize here the laser beams that are coming out here. It's the only sensor that Dolly has, just for simplicity. And my simulation crashed, of course. While I'm opening it up again. So Dolly has one sensor and has a few different actuators. It's mainly two wheels that do differential drive steering. And it has also a passive caster wheel, and but the wheels really that are moving are the two wheels that do differential drive. And the logic that is really connecting all of it is just one node that has a follow logic. And it says, find me the closest point in front of me, and then send me the direction that you want to go, and create a command for the wheels, and the wheels are going to move in that direction. I'm just gonna restart the simulation here. So the loop that I'm going to show you in my slide zone is the things go from the laser to the follow node. Where is it? Okay, I hope you're seeing it again. Let's go back there. Okay, so there's the laser, there's the wheels, and then there's the follow node, and the flow of information is from the laser senses some data, it sends it to the follow node, it makes a decision about what's the closest thing, and sends a command to the wheels to go move in that direction. Then the wheels move, and when the wheels move, the laser readings change, right? Because there's like a different organization of the world in front of it, and then it does the cycle. So it's called like the sense, think, act cycle in robotics that is very common. And we also have a podcast sponsored by Open Robotics and hosted by my colleague Audro that is called Sense, Think, Act, that everybody should listen to. Just a little product placement here. But continuing, so we have the Sense, Think, Act cycle, super simple, and most applications will have some aspect of it. So the part that is using ROS2 is this side here. Everything that is in purple, that's above this line here, is using ROS2. So there are ROS2 scans going into this follow node, and there are ROS2 commands coming out of the node. And everything that is below the line is being simulated by Gazebo. So the laser readings are simulated by Gazebo, the wheel movement is simulated by Gazebo, the movement that the wheels do, and then that changes the laser readings, everything here is in Gazebo. So the important thing to understand is that everything that is above the purple line is not simulation specific. That's the code that you would take and move to a physical robot, and everything that is below is simulation specific that is helpful for your testing, but it's not stuff that will go into your final application. So when thinking about testing, what are we really interested in testing here for the system, right? Like, we don't want to be testing the laser. Is the laser generating correct data? Is the laser, when we move the laser, the readings change accordingly? Are things in the correct frame? This is not what a typical user would want to test, because that's like what we as the simulator developers test, right? That's the responsibility of you assume that the laser is doing its job correctly. The same thing with the wheels. We don't want here to be testing, like, are the wheels moving in the correct speeds when I give a certain command? What we really want to understand with the test setup is whether the follow node is doing what it should. Right, so that's why I put it here in green, like the follow node is what we want to test, and the yellow parts I didn't put it in red, like it's yellow, you don't want to be testing them. You may want to set up some tests just to know that you set up your simulation correctly, just as sanity checks, but that's not the goal of your simulation. You're not setting up the simulation to test that the simulator is generating the correct data. And then people may say like, well, if I just want to test the follow node, why don't I just like create some custom, like by hand, some custom laser scans with different readings and then check on the other ends that it generates the correct commands, right? Like, why do I need a whole simulator attached to it? Well, if you want to test some simple cases, and this is probably a very simple case, it's probably fine for you to just do unit tests of your nodes. But as soon as you get into more complex behaviors where the robot is moving and then the laser scans are changing in a realistic way, or you have different sensors like cameras that have very rich images, or you want to do sensor fusion with various sensors, the simulator comes in to fill that gap and generate all of that synthetic data in a coherent way, similar to the real world for you. So you have to know when you're testing your systems, right? Like, do I need a simulator? Maybe I can just do some unit tests on my nodes and that's fine. Maybe parts of my system can be unit tested. Parts of my system need to be system tested with the entire simulator. So it's important to know how to use the tools for the correct things that they need to be used, right? So this is the general idea of the system. Let's get into the specifics. How is this implemented? So the whole simulation is launched with ROS Launch. And then ROS Launch launches the world of the simulation itself. It's an SDF world. For this example here, I'm launching a world that has like all of this environment around it. It has the woman there, it has the tables, the water. But for testing, you probably don't want such a complex world, right? Like you really want to do something minimal, because that test is going to be running on every single commit that you do, on every single code change that you do. So we want the most simple thing that still exercises your system. So for testing, you're probably going to launch a different world. And this world includes everything but the robot, right? So where does the robot come from? The robot comes from a spawn process that we launch with ROS. So it's a ROS specific process that calls into the simulation and spawns the robot. And the good thing of keeping the robot separated from the world SDF is that the robot we can spawn it into different worlds, we can spawn it into different scenarios. And the good thing about using ROS is that you can spawn, like here I happen to be spawning from a file that I installed with the package, but it could be coming from a ROS topic, it could be coming from a ROS parameter, it could be a URDF, it doesn't need to be an SDF. So you can do, you have multiple options to spawn that robot into simulation. But at this point, there's no ROS going on except for really the spawn node. It spawns something that is only in the simulation. The laser and the wheels here are just inside the simulation. And then we spawn the follow node that is pure ROS2, but right now things are not connected to each other. The laser and the wheels here, they're just inside the simulation, they're not talking to ROS. So we also have to spawn a ROS ignition bridge that bridges the internals of the simulator, like the communication that is internal to the simulator using ignition transport to the ROS2 topics here on this end. So this is where really the ROS2 communication is going on, and down here there's nothing. And you know, you wouldn't need the spawn node or the ROS ignition bridge when you move this logic to a physical robot. All you would really need to take is the follow node. So this is just a high-level overview of what is happening. Let's jump into the code to see how this actually is implemented. So, you know, just to remind everybody, the robot is here, moves forward, goes behind the closest thing in front of it. So close the simulation. Let's jump into the code. So I have here a Qualcomm workspace, and I have the Dolly package. So this is the package that...
Are we supposed to see the console?
Oh, yes. I couldn't share my... Thank you. I couldn't share my entire window, so I'll have to share window by window. So first, the browser here. So this is the repository where the tests live. If people want to take a look closer into the code or copy the code and kind of adapt it to your own use case, this is the ROS2 package that we're going to be looking into. It's called Dolly Tests. It's inside the top-level Dolly repository where the Dolly simulation and all of this other stuff is. Like the follow node is this package that is here separate. It's common practice to keep your tests separate from all of your other packages, just so if people who are using the follow node, they don't need to also bring the test dependencies and compile all of that and so on. So just keep the test in its own package. So we're going to be looking into this package here. So I'll have to unshare my screen again and now share my console. Okay. So, okay, this is my console here. So this is my workspace. It's a Cocon workspace specifically for this. And then inside it, I have the Dolly package. And you can see that it's exactly the same stuff that we saw on GitHub just now. So if you go inside Dolly tests, this is what it looks like. So we have our empty world. Remember that I said that we don't want to launch a very complex world for a test. We want to launch the minimal world that allows us to reproduce what we are trying to reproduce. So this is the world. We have the test code explicitly, which is the C++ code that is going to be, we are going to be loading it instead of the simulator itself. So instead of launching Gazebo with a GUI and a bunch of other things that you would need for development usually, this will launch the simulator just with the bare minimum that you need, and it's going to give you control on the body of the C++ code to step the simulation, check all of the ground truth values that you can't get in the real world, but in simulation it's really easy to get the ground truth and check where the robot is, check if the robot is behaving like you expected. And the other important file is the launch file that launches everything together. So first, oh yeah, and it's also important now because we're talking about GitHub, setting up GitHub CI. So you can see here on GitHub workflows, we have our GitHub actions, and we have a little bash script that is going to be run on every commit. So we're going to look into that as well. So hopefully I can quickly walk over a few of these files. So the first one that I'd like to show you is the SDF world. So as you can see, one thing that I always recommend people to do on tests is to run with real-time factor 0, which means that it runs as fast as possible, because you don't want it to be running like in real time. There's no human looking at it and really interacting with it. So you just want it to run really fast. And try to set your step size to as high as you can while the simulation is still stable. I put it here at 5 milliseconds. I could probably have put it a little bit higher, but you have to make sure that you don't make the simulation too unstable. But the higher this is, the faster the simulation is going to go, the faster your tests are going to turn around, and the less CI time you spend, right? Even though GitHub Actions is free, you probably want your commits to give your results fast. And then another thing is to keep your plugins to a minimum. Like here, we really only need the physics to move the robot. We need the user commands because we're spawning the robot, and we need that to receive it. And we need sensors to generate the sensor data from the LiDAR. And then as for other models, we only need a ground plane for the robot not to fall. And it doesn't even need a visual. We don't need a light. We don't need anything else. If you open this world, you're not going to see anything because it's all dark, because the robot works in the dark. So we don't need that extra complexity of adding a visual, adding a light, and so on. So another file that I'd like to look into is the test. Test follow. So how is the test set up? This is a C++ file. We are using gtest. So people familiar with gtest are probably familiar with these test macros that you can use to set up your tests. Just to give a high-level overview of how things are set up, we are using this Gazebo test fixture class that is available on all of the supported Ignition Gazebo versions, so from Citadel to Fortress. So you start this fixture, and this is going to be your simulator. that are going to be loading a world and stepping it and simulating without the extra overhead of a GUI and so on. Then the way that we set up the fixture is we give it some callbacks that are going to be called in specific moments of the simulation. So here we're doing configure and post update. We can use configure. It's only called once at startup to do things like getting data that you want to get once, like the world entity, for example. And the post update is for checking things continuously, right? One trick that I always tell people to do is, since the robot is going to be spawned by ROS, it's synchronous. You may not get the entity is not going to be there from the start. So a lot of people tend to put here like by iteration, so and so, the entity must be there. But you remember that you want this to run on GitHub Actions, like hardware. You don't know where it's running, what machines it's running in. They may be very slow, they may be very fast. And since this is all asynchronous, it's going to ROS, it's going back. Don't hard code, if you can, any timing data into your tests. So what I'm doing here, I'm just like checking until the entity is null. I keep doing this post update, and then I get the entity to actually work with it. So I tried not to hard code any specific timing because it's really hard. Then you have to remember to call the finalize call. This is the moment when the configure callback is called. This is where we put some safety, some time safeties, but with a lot of slack. We run the simulation, so we step the simulation a few times until we see that we got the entity that was spawned by ROS. And we sleep a little bit in between all of them, and it's important to put a timeout there, but like the timeout here is 3 seconds, and if your CI is taking more than 3 seconds to do this, then there's probably a problem, right? It's 30 times 100 milliseconds. So it's a very high timeout. But it's good to be safe, because if there's a problem with your test and you don't put a timeout, it's just going to hang. GitHub Actions can hang for like 24 hours. So you may just be using resources there for no reason. So, we start checking that the robot is not moving because the robot is alone in the world. Then we spawn another object in front of it so it can follow. Then we go through the whole process of running the simulation again in a loop, a few iterations, and waiting for that object again to be spawned. Then we check, well, the object was just spawned, the robot hasn't had time to move yet, and now finally we start stepping and we see that the robot is moving. And we start checking, for example, that the robot is going forward. The pose X is like the next pose X is higher always than the previous one. We are also spawning the robot a little bit to the right, so the robot is going to the right, so we can check that the Y is changing and the yaw is changing, and we can sanity check that like none of the other elements are changing. So just a very simple test to show some of the things that you would test in your real use cases. Then just one other thing that I wanted to show you. So I think we're running out of time, so it's going to be hard to show the launch file in detail. But just for you to have an idea of what's going on, this is using ROS Launch Testing. So it's very similar to launching the simulation, but you have to launch the test executable instead of the simulation. But then the spawn node and the bridge node, these are all things that you would run during a regular simulation. It's the exact same spawning. Then the follow node is the important one, and you just launch it like you would launch not in a test. And from the ROS side, it's actually just checking that the test runs until the end and returns a success code or not. We are not doing anything more complex in this example. For the ROS launch testing, we're not testing the contents of the ROS topics or anything like this. We're really just focused on the simulation behavior. Then just to show people the GitHub Actions. So this is what it looks like. We're launching with like Ubuntu Foco with Ignition Fortress and ROS rolling. Then we like we're checking out the Dolly code itself, and we're also checking out ROS ignition, because right now there's no ROS ignition binaries on rolling using Fortress. So you also have to compile that from source. And we run this bash script here. And the bash script is, so some interesting things that you have to put here. I didn't show you, but in the C++ code, we have a line to call to use headless rendering. And that's important because GitHub Actions doesn't have GPUs. So from Ignition Fortress, you can use EGL to do headless rendering. So those laser scans are actually being generated without a GPU when running on GitHub Actions. So these environment variables help you make sure that the headless rendering is working correctly. Then we install some tools, use ROSDEP to get our dependencies. And finally, we do Cocon build, which builds Dolly and ROS ignition, remember, and also we do our Cocon test. And important, a lot of people forget to put Cocon test result in their GitHub Actions. If you don't do this, it's never going to return a fail code, because Cocon test by itself doesn't return a fail code. So if you want the actions to fail when the tests fail, you need this call. That's a super high level overview. If people have questions, I recommend that you try out the package, take a look, clone it, try to adapt it to your own use cases and see how it goes. That's it. Any questions? Okay, I see here James Bucky. What is the best way to contribute to the community? Okay, yeah. So like we get this question a lot. There are many ways that you can get involved in the Gazebo and ROS communities. One way is just like adding documentation. You can, whenever you see a bug, you ticket a bug, or you can go to ROS Answers and Gazebo Answers and answer questions from other people in the community who may be having problems. If you want to contribute codes, we have our code contribution guides out there. I don't know if other people here have other ideas and suggestions for James. But these are some of the things I can think of. Yeah, you're welcome. Like, looking forward to seeing you in our contribution channels. Any other questions? It could be a question for me. It could be a question for Kenny.
I don't have a question, actually. I just want to say that I think that this is really nice. I have used Unity testing for simulation, but the way that I've done in Gazebo was to use the system calls to launch the G server and to do everything. So using terminal commands. So I think that fixture would be a really nice thing to use. Yeah, I'll probably try it out.
Cool. Yeah. I've seen a lot of people doing that too. That's a valid way. It adds more complexity because everything is more asynchronous, and you can't like step in the simulation. You have to send messages into the simulation to step it. So it's a little bit more involved, and using the test fixture, it tends to be simpler because you can step very carefully and check things directly there in the process of the simulator.
I have a question for Kenny. Great talk and all the cool stuff you guys are doing. It's awesome. I was wondering about when you were doing the online testing where people can log in and have SSH access to the robot. I was wondering if I guess what the reason was for giving them SSH access as opposed to like having them send their code, like a binary blob of their code or something, and then someone there could or automatically have it go to the robot and run. Is there a particular use case for the SSH, or is it just a more convenient somehow?
Oh, that's a good question. I think we provided the SSH access so that teams can test and work on their solutions in real time with the robot online. And so essentially they would be doing like a video video call there, we set up a camera that provided feeds of the robot. And so they could see the robot, they could run their commands, and they could not only log the data themselves, but actually interact and see what errors are coming through. And there were definitely challenges with that, just having different people to compile and run their the software on the same computer. But it somewhat worked okay. But in the future, yeah, we're looking for ways to make it less cluttered in that sense, and maybe just providing options for us to automatically test, but then just sending executables to us.
Yeah, I was thinking like, doing SSH when you have low or slow internet is really tough, and it's great to be able to interact with the robot in real time, but I think part of like improving the reliability would be my suggestion would be to have them send this asynchronously, and then you have a queue of like, okay, here are all the submissions, and we run them whenever we're ready, and there's someone to run these batches of tests, and then you record all the sensor information and in a bag file or something, and it's up to them to improve on that for their next submission, right? To get all the
makes sense. Yeah, thanks for sharing. Appreciate that.
Absolutely.
Okay, any other questions? We've had a few in the chat. I don't know about like the combination of Galactic and Fortress. So just for the record here, for people who are not want to have access to chat later, all of the pairing between ROS and Ignition versions, and it's the same for Gazebo Classic, they are dictated by rep 2000 for ROS 2 and by rep 3 for ROS 1. And to release packages in the ROS farm, we have to like release the packages that correspond to that official combination, and that's so that we don't need to support like a big number of different combinations, and also so that the community doesn't split and we have like some downstream packages that build one combination or build the other. So we have the official pairings, but you can build from source the ROS Ignition with different combinations. We make sure on the source code and there are instructions there that you can follow to do these different combinations. And in the past, we've released alternative dabs on a different build farm, not the ROS build farm, but the OSRF farm. If there is enough interest, we could look into doing that too. At this point for Galactic, I think it's so close to EOL that it may not be worth at this point. But. So we have 2 minutes. I just want to make sure that we go over the news here real quick that Kat curated for us. So there's a couple of tutorials added by the community, good stuff, like if you're interested in Ignition with ROS 2 control, spoiler alert, there may be a presentation coming up in a future community meeting, and stay tuned. But just to get a taste of it, there is this tutorial here. There is like a visualization that I did for contributions to Gazebo over time. There are like ROS World videos are there. Like there's an internship for people who are in the US and you're interested in working with Ignition. The EOL notes for Ignition Dome, and some other like posts for Ignition about like the platforms that we support, if you care about that. Like do we support Foco or Jamie, or where should we get our software? And also there's a post about EGL that I mentioned during the presentation here today. So if there's nothing else that people want to talk about, we can wrap it up. Sounds good. Thank you again, Kenny, for joining. Thank you, everyone, for being here. And see you next month. Bye.
Thank you. Goodbye.